Recordings rolling. It is Friday, April 25th. Ooh, you guys get to learn something special today. You guys learned about dark matter and dark energy, which are two different mysteries in the universe. So watch a TED Talk today. You guys all have a quarter page. You guys got this quarter page. Just make sure you turn this quarter page to the grade tray. That'll be your first post-interim grade. So go to the last eighth of the school year. These relativity puzzles, actually, it's two different assignments. There was this speed of light cogwheel puzzle, and these relativity puzzles. Now, most of you guys turned this in already, because if you haven't turned them in yet, you got to get them in today if you want that score to show up on your interim. So get those grades with the grade book. We're going to have about 10 spare minutes at the end of class today, so I'll roll a couple of Veritasium videos, one on how magnetism can be, or electromagnetism actually, can be explained by theory of relativity. Another one where he goes through some common questions like, could this or that go faster than the speed of light, and why that would not work. And so for this first question, actually, this dark energy idea has to do with the size of the universe. Now, if you look at distant galaxies, let's go back about 100 years ago. This guy named Edwin Hubble, who was looking at distant galaxies, and noticed that they were almost all redshifted compared to Earth. In fact, the further away they were, the more redshifted they were. And that's related to this here. So the Doppler effect for light. Guys, redshifting means that the galaxies are moving how to us? Towards us or away from us? Away, right? So some kind of relative motion where the galaxies move away. Okay? In fact, if they're further away, they're moving faster. That tells you something about how the universe is expanding. So our model right now is that the universe is expanding universally everywhere. So space between galaxies and galaxy clusters is growing. So there's some parts of the universe we'll just never be able to access or see. It's beyond the observable universe just because it's moving so fast that the light will never reach us. Okay. All right. So if you go back to pretty much any time in the 20th century, say the 1990s, back when I was in school, we talk about what's the size of the universe as a function of time. Right? Size is a function of time. Okay. Now, if everything's moving away from us, you can rewind the clock and say, well, when was everything sort of the same place, same time? That looks about 13.8 billion years ago. Okay. So that is part of the Big Bang theory, right? That's right. And there's more evidence for the Big Bang theory, but that was one big piece of evidence. Now, if matter gravitationally attracts and the universe is expanding in some Big Bang about 14 billion years ago, put all that together, and you say, like, what's the ultimate fate of the universe? Like, what's the size of the universe as a function of time? There were three main hypotheses that were floating around for most of the 20th century. And one of them goes like this. Well, maybe about 14 billion years ago, there's a Big Bang, but because everything gravitationally attracts, it's all going to pull together, and the universe, well, might end in the Big Crunch. And then, who knows, maybe it'll bang again, and maybe this could be an infinite process or some version of that. Right? That's one hypothesis. Okay? It's kind of analogous to if you throw a ball up in the air, it just comes back down and lands in your hand again, lands on the ground. But take that analogy. Ooh, could you throw the ball in the air fast enough so that it reaches escape velocity and flies away from the Earth forever? And that might be a curve that looks something more analogous to this one, where, yeah, everything's still gravitationally attracting, so the expansion would be slowing down, but it could maybe expand forever. Okay, so here, I think I need a title on this chart. Let's call it a size of the universe. Okay. These are, again, a couple hypotheses. Right? Or if you take that throw the ball in the air analogy, you could throw it just so that it orbits the Earth. And that would be kind of analogous to what if you had an asymptotic size that the universe was reaching. So it's still expanding, still slowing down, still concave down, but sort of reaches an asymptotic size and kind of peters out like that. Okay? Right, so those are the main three hypotheses for most of the 20th century. Oh, yeah.
You know what concave rhymes with?
What?
Conclave. Dead Pope.
That is true. All right, we got some other references tying here. Now, about 20, 30 years ago, so about the year 2000, there were different teams of astronomers that set out to answer this question, which curve are we on? And they all reached the same conclusion independently of each other. And weirdly enough, the answer was none of the above. So if it's not any of those three, then what's actually going on with size of the universe? So hang on to that question, because that's one of these here. So here you go. Dark matter, dark energy. You guys got all quarter pages?
Particle physicist, I study the elementary particles and how they interact on the most fundamental level. For most of my research career, I've been using accelerators such as the Electron Accelerator at Stanford University just up the road to study things on the smallest scale. But more recently, I've been turning my attention to the universe on the largest scale. Because as I'll explain to you, the questions on the smallest and the largest scale are actually very connected. Okay? So I'm going to tell you about our 21st century view of the universe, what it's made of, and what the big questions in the physical sciences are, or at least some of the big questions. So recently, we have realized that the ordinary matter in the universe, and by ordinary matter, I mean you, okay? Me, the planets, the stars, the galaxies. The ordinary matter makes up only a few % of the content of the universe. Almost a quarter, or approximately a quarter, of the matter in the universe is stuff that's invisible. By invisible, I mean it doesn't absorb in the electromagnetic spectrum, it doesn't emit in the electromagnetic spectrum, it doesn't reflect, it doesn't interact with the electromagnetic spectrum, which is what we use to detect things, it doesn't interact at all. So how do we know it's there? We know it's there by its gravitational effects. In fact, this dark matter dominates the gravitational effects in the universe on a large scale. And I'll be telling you about the evidence for that. What about the rest of the pie? The rest of the pie is a very mysterious substance called dark energy. More about that later, okay? So for now, let's turn to the evidence for dark matter. In these galaxies, especially in a spiral galaxy like this, most of the mass of the stars is concentrated in the middle of the galaxy. This huge mass of all these stars keeps stars in circular orbits in the galaxy. So we have these stars going around in circles like this. As you can imagine, even if you know physics, this should be intuitive, okay? That stars that are closer to the mass in the middle will be rotating at a higher speed than those that are further out here, okay? So what you would expect is that if you measured the orbital speed of the stars, that they should be slower on the edges than on the inside. In other words, if we measured speed as a function of distance, this is the only time I'm going to show a graph, okay? We would expect that it goes down as the distance increases from the center of the galaxy. When those measurements are made, instead what we find is that the speed is basically constant as a function of distance. If it's constant, that means that the stars out here are feeling the gravitational effects of matter that we do not see. In fact, this galaxy and every other galaxy appears to be embedded in a cloud of this invisible dark matter. And this cloud of matter is much more spherical than the galaxy themselves, and it extends over much wider range than the galaxy. So we see the galaxy and fixate on that, but it's actually a cloud of dark matter that's dominating the structure and the dynamics of this galaxy. Galaxies themselves are not strewn randomly in space. They tend to cluster. And this is an example of a very actually famous cluster, the Coma cluster. And there are thousands of galaxies in this cluster. They're the white, fuzzy elliptical things here. So these galaxy clusters, we take a snapshot now, we take a snapshot in a decade, it'll look identical. But these galaxies are actually moving at extremely high speeds. They're moving around in this gravitational potential well of this cluster. Okay, so all these galaxies are moving. We can measure the speeds of these galaxies, their orbital velocities, and figure out how much mass is in this cluster. And again, what we find is that there is much more mass there than can be accounted for by the galaxies that we see. Or if we look in other parts of the electromagnetic spectrum, we see that there's a lot of gas in this cluster as well. But that cannot account for the mass either. In fact, there appears to be about 10 times as much mass here in the form of this invisible or dark matter as there is in the ordinary matter, okay? It would be nice if we could see this dark matter a little bit more directly. I'm just putting this big blue blob on there, okay, to try to remind you that it's there. Can we see it more visually? Yes, we can. And so let me lead you through how we can do this. So here's an observer. It could be an eye, it could be a telescope. And suppose there's a galaxy out here in the universe. How do we see that galaxy? A ray of light leaves the galaxy and travels through the universe for perhaps billions of years before it enters the telescope or your eye. Now, how do we deduce where the galaxy is? Well, we deduce it by the direction that the ray is traveling as it enters our eye, right? We say the ray of light came this way, the galaxy must be there. Okay. Now, suppose I put in the middle a cluster of galaxies, and don't forget the dark matter, okay? Now, if we consider a different ray of light, one going off like this, we now need to take into account what Einstein predicted when he developed general relativity. And that was that the gravitational field due to mass will deflect not only the trajectory of particles, but will deflect light itself. So this light ray will not continue in a straight line, but would rather bend and could end up going into our eye. Where will this observer see the galaxy? You can respond. Up, right. We extrapolate backwards and say the galaxy is up here. Is there any other ray of light that could make it into the observer's eye from that galaxy? Yes, great. I see people going down like this. So a ray of light could go down, be bent up into the observer's eye, and the observer sees a ray of light here. Now take into account the fact that we live in a three-dimensional universe, okay, three-dimensional space. Are there any other rays of light that could make it into the eye? Yes, the rays would lie on I like to say, yeah, on a cone. So there's a whole rays of light on a cone that will all be bent by that cluster and make it into the observer's eye. If there's a cone of light coming into my eye, what do I see? A circle, a ring. It's called an Einstein ring. Einstein predicted that, okay? Now, it'll only be a perfect ring if the source, the deflector, and the eyeball in this case, are all in a perfectly straight line. If they're slightly skewed, we'll see a different image. Now, you can do an experiment tonight over the reception, okay, to figure out what that image will look like, because it turns out that there is a kind of lens that we can devise that has the right shape to produce this kind of effect. We call this gravitational lensing. And so this is your instrument, okay? But ignore the top part. It's the base that I want you to concentrate, okay? So actually at home, whenever we break a wine glass, I save the bottom, take it over to the machine shop, we shave it off, and I have a little gravitational lens, okay? So it's got the right shape to produce the lensing. And so the next thing you need to do in your experiment is grab a napkin. I grabbed a piece of graph paper. I'm a physicist, so a napkin, draw a little model galaxy in the middle, and now put the lens over the galaxy, and what you'll find is that you will see a ring, an Einstein ring. Now move the base off to the side, and the ring will split up into arcs, okay? And you can put it on top of any image on the graph paper. You can see how the lines on the graph paper have been distorted. And again, this is a kind of an accurate model of what happens with the gravitational lensing. Okay, so the question is, do we see this in the sky? Do we see arcs in the sky when we look at, say, a cluster of galaxies? And the answer is yes. And so here's an image from the Hubble Space Telescope. Many of the images you were seeing earlier from the Hubble Space Telescope. Well, first of all, the golden-shaped galaxies, those are the galaxies in the cluster. They're the ones that are embedded in that sea of dark matter that are causing the bending of the light to cause these optical illusions or mirages, practically, of the background galaxies. So the streaks that you see, all these streaks, are actually distorted images of galaxies that are much further away. So what we can do then is, based on how much distortion we see in those images, we can calculate how much mass there must be in this cluster. And it's an enormous amount of mass. And also you can tell by eye, by looking at this, that these arcs are not centered on individual galaxies. They are centered on some more spread out structure. And that is the dark matter that is in which the cluster is embedded. Okay, so this is the closest you can get to kind of seeing at least the effects of the dark matter with your naked eye. Okay, so a quick review then, okay, to see that you're following. So the evidence that we have that a quarter of the universe is dark matter, this gravitationally attracting stuff, is that galaxies, the speeds with which stars orbit in galaxies is much too large. It must be embedded in dark matter. The speed with which galaxies within clusters are orbiting is much too large. It must be embedded in dark matter. And we see these gravitational lensing effects, these distortions that say that, again, clusters are embedded in dark matter.
Ooh, all right, so that's the dark matter half of this presentation. Everything after this pause point, she's going to talk about this big old wedge right here called dark energy. Okay, so give you guys a recap. She's talking about Einstein rings. Here's a really nice photograph of an Einstein ring. So this is some galaxy out in the world. Now, if you were next to this galaxy, it would just look like a regular galaxy. It wouldn't look like a ring at all. Looks like a ring to us, probably because there's dark matter between us and that object right there. Right. So here's her recap for dark matter, evidence for dark matter. It's got all these points of evidence and this graph. Okay. Now, everything after that pause point, she's going to talk about a completely different idea called dark energy. So dark as in dark to our vision, dark to our knowledge. We don't know what this is, but this right here, this dark energy is going to address this question, something about the size of the universe. Yeah, here's the three main hypotheses floating around the 20th century. But I told you that, guys, that what they end up concluding is none of the above. So what is none of the above? All right, you guys ready for that? Here we go.
Okay, so now let's turn to dark energy. So to understand the evidence for dark energy, we need to discuss something that Stephen Hawking referred to in the previous session, and that is the fact that space itself is expanding. So if we imagine a section of our infinite universe, okay, and so I put down 4 spiral galaxies, okay, and imagine that you put down a set of tape measures. Okay, so every line on here corresponds to a tape measure, horizontal or vertical, for measuring where things are. If you could do this, what you would find that with each passing day, each passing year, each passing billions of years, okay, the distance between galaxies is getting greater. And it's not because galaxies are moving away from each other through space. They're not necessarily moving through space. They're moving away from each other because space itself is getting bigger, okay? That's what the expansion of the universe or space means. So they're moving further apart. Now, and what Stephen Hawking mentioned as well is that after the Big Bang, space expanded at a very rapid rate. But because gravitationally attracting matter is embedded in this space, it tends to slow down the expansion of the space, okay? So the expansion slows down with time. So in the last century, okay, people debated about whether this expansion of space would continue forever, whether it would slow down, will be slowing down, but continue forever, slow down and stop, asymptotically stop, or slow down, stop, and then reverse, so it start to contract again. So a little over a decade ago, 2 groups of physicists and astronomers set out to measure the rate at which the expansion of space was slowing down, okay? By how much less is it expanding today compared to, say, a couple of billion years ago. The startling answer to this question, okay, from these experiments, was that space is expanding at a faster rate today than it was a few billion years ago.
Ooh. All right, so she just told you the answer. So what that would look like on a graph, size versus time, it's actually something more like this. Something more like this. Okay. So yeah, there was a Big Bang some 13, 14 billion years ago. The universe is expanding. Not only is it expanding, it's actually expanding faster, faster, faster. Okay. Now, why would that be? Is there some good theory for why? No, there isn't. It's a complete mystery. But mathematically, you can treat this as an energy equation in Einstein's equations.
Okay, so the expansion of space is actually speeding up. This was a completely surprising result. There is no persuasive theoretical argument for why this should happen. Okay, no one was predicting ahead of time this is what's going to be found. It was the opposite of what was expected. So we need something to be able to explain that. Now, it turns out in the mathematics, you can put it in as a term that's an energy, but it's a completely different type of energy from anything we've ever seen before. We call it dark energy, and it has this effect of causing space to expand. But we don't have a good motivation for putting it in there at this point. Okay, so it's really unexplained as to why we need to put it in. Now, so at this point, then, what I want to really emphasize to you is that, first of all, dark matter and dark energy are completely different things. Okay, there are really 2 mysteries out there as to what makes up most of the universe, and they have very different effects. Dark matter, because it gravitationally attracts, it tends to encourage the growth of structure. Okay, so clusters of galaxies will tend to form because of all this gravitational attraction. Dark energy, on the other hand, is putting more and more space between the galaxies, makes it the gravitational attraction between them decrease, and so it impedes the growth of structure. So by looking at things like clusters of galaxies and how they, their number density, how many there are as a function of time, we can learn about how dark matter and dark energy compete against each other in structure forming. In terms of dark matter, I said that we don't have any, really persuasive argument for dark energy. Do we have anything for dark matter? And the answer is yes. We have well-motivated candidates for the dark matter. Now, what do I mean by well-motivated? I mean that we have mathematically consistent theories that were actually introduced to explain a completely different phenomenon, okay, things that I haven't even talked about, that each predict the existence of a very weakly interacting new particle. So this is exactly what you want in physics, where a prediction comes out of a mathematically consistent theory that was actually developed for something else. But we don't know if either of those are actually the dark matter candidate, okay, one or both, who knows, or it could be something completely different. Now, we look for these dark matter particles because after all, they are here in the room, okay, and they didn't come in the door. They just pass through anything. They can come through the building, through the earth. They're so non-interacting. So one way to look for them is to build detectors that are extremely sensitive to a dark matter particle coming through and bumping it. So a crystal that will ring if that happens. So one of my colleagues up the road and his collaborators have built such a detector, and they've put it deep down in an iron mine in Minnesota, okay, deep under the ground. In fact, in the last couple of days, announced the most sensitive results so far. They haven't seen anything, okay, but it puts limits on what the mass and the interaction strength of these dark matter particles are. There's going to be a satellite telescope launched later this year, and it will look towards the middle of the galaxy to see if we can see dark matter particles annihilating and producing gamma rays that could be detected with this. The Large Hadron Collider, a particle physics accelerator that will be turning on later this year. It is possible that dark matter particles might be produced at the Large Hadron Collider. Now, because they are so non-interactive, they will actually escape the detector. So their signature will be missing energy, okay? Now, unfortunately, there's a lot of new physics whose signature could be missing energy. So it'll be hard to tell the difference. And finally, for future endeavors, there are telescopes being designed specifically to address the questions of dark matter and dark energy, ground-based telescope, and there are 3 space-based telescopes that are in competition right now to be launched to investigate dark matter and dark energy. So in terms of the big questions, what is dark matter? What is dark energy? Big questions facing physics. And I'm sure you have lots of questions, which I very much look forward to addressing over the next 72 hours while I'm here. Okay, thank you.
All right, so there's a synopsis right there. Just make sure you have that quarter page turned to the gray tray. Again, we got about 10 spare minutes here. I'm going to roll a couple of Veritasium videos. Also, double check focus, make sure you got everything in this class and your other class for that matter, and that'll be a wrap on this recording.